Hello, hope you're having a great conference. Tim Sandle here, and I've got a presentation for you which is looking at environmental monitoring and environmental control. So let's get the slides. Here we go. Right, so this is all about fine-tuning your environmental monitoring program. So in this session, I want to consider what my environmental monitoring can actually show, the use of risk assessments and why we might need them. What's the consequence of doing a poor risk assessment? What is our data? What is our data signal? What can lead to bad data? What's wrong with our methods? Why should we trend? What data integrity issues are there? And we'll also have a look at some case studies. It's important to bear in mind that environmental monitoring is no substitute for poor controls. The individual elements of the monitoring program should never be considered in isolation. Although individual results are important, like understanding batch-specific events, we often get a more meaningful picture from trending our data. Risk assessment is fundamental to environmental monitoring. This includes identifying locations where microorganisms are most likely to occur, and then considering the different ways that contamination can be transferred from clean room to product, for example, or from a person to the product, or cross-contamination between different products. And risk assessment can also help us to develop a good environmental monitoring locations and frequencies of monitoring. So we can say to regulators, these are why we've decided on these locations, and these are what the locations are telling us, if the data is good or if the data is poor. Risk assessment also helps us to establish alert and action levels, and also gives us a degree of guidance should out of limits events occur. Feeding into the risk assessment process through things like change control and building up process knowledge and using scientific understanding all help us to revise and to reflect upon and to strengthen our risk assessments. They can also guide us with creating the appropriate documentation and also with educating and training personnel. Risk assessment also helps us to assess the contamination events. How severe is the contamination? How likely was the contamination to occur? Would the microorganisms survive in the product? What are the potential vectors for spreading the contamination around? So there's lots of fundamentally important information that we can derive from such risk assessments. So we can also use risk assessment to determine where contamination is most likely. And here's an example of such a risk chart. So we're considering the amount of microbial contamination at a certain point on a source. So this could be a surface, for example. Then we're also considering the ease of dispersion of that contamination from that source. So how likely is an operator to put their hand onto the surface and transfer that contamination? Or similarly, if that contamination was to be dispersed into the airstream. Then we're considering with risk factor C the ease of movement to contaminate the actual product. And we're also considering how close the source is to the product. So we can start to build up on these issues. We can develop things like numerical scoring systems, or we can use things like low, medium, and high. But all of this comes into assessing the likelihood of the actual product being contaminated from the occurrence of microorganisms within our manufacturing environments. We also need to acknowledge that people are the biggest risk within clean rooms. People touch things, people can sometimes misbehave, but also the complexity of the human skin microbiome The human body is composed of different niches. There are variances in moisture, pH, and there's also sebaceous areas. And the clean room gown should be thought of as a large filter, and it's going to filter around 80 to 90% of the contamination. If we double gown, then we can introduce a further factor to reduce the contamination. However, it still remains that an element of contamination will be shed, will be released into the environment. So controlling the way people move and always putting up barriers where we can to separate people from product is of great importance. Regulators often criticise poor risk assessment. So this can be the so-called satellite navigation risk assessments, where you go into the room and say, how do we get to a low risk situation? And these are kind of fairly artificial risk assessments. So we need to work on good, scientifically and technically sound risk assessments. So understand product risks. So what's our product formulated with? What happens if particular species of microorganisms have the potential to interact with particular product formulations? We need a thorough understanding of our facilities, the material flows, the product flows, the people flows, which can all help us to understand the significance of a given risk. And we need to really put all of this together into a framework, and if we do that, we're on the side of having a good risk assessment, and we can avoid that poor risk assessment scenario. Risk assessments can also be weak if they're not looking at things holistically. So one of the things that EU GMP Annex 1 is getting at is to look at things holistically. So what the annex is trying to get to here is to say that if you've got things occurring in grade D, let's say the bioburden starts to build up, risk assessments can also be weak if they're not looking at things holistically. So one of the things that EU GMP Annex 1 is getting at is to look at things holistically. So what the annex is trying to get to here is to say that if you've got things occurring in grade D, let's say the bioburden starts to build up, then there's a realistic opportunity for that to transfer into grade C. And then if you have an aseptic core, then you start having problems in grade C, particularly around airlocks, transfer hatches, changing rooms, equipment flows. Then you have the opportunity for transferring that equipment into the aseptic core. Other weaknesses with risk assessments are not giving equal weighting to people, surfaces and air, and understanding air distribution. Risk assessments that are good are based on data, so we accumulate information, we use scientific principles, we use proactive assessments wherever we can, and also we don't just put these things on shelves to gather dust, but we look at them on a regular basis. Now, one thing that I've mentioned before is the activity of transfer, and this is one of the biggest weaknesses in the clean room. So how do items get from our warehouse into our manufacturing areas and then through our manufacturing areas, moving through the clean room cascade and ending up where they're going to be used? So we need to map out this transfer process. We need to understand where our different wrappings are going to be removed. Where should we be applying different types of disinfectants? Where do we make sure there is no outdoor packaging coming in? How do we ensure that items are correctly dry? These are all fundamentals that we need to use risk assessment to help us to answer. Risk assessments can also be weak if they're over-reliant upon environmental monitoring. So environmental monitoring can be very useful, but its detectability is limited. We're only going to grow certain microorganisms that can grow with that particular culture medium formulation, that are going to grow at the temperatures at which we elect to incubate the medium at. And even for organisms that would normally grow under one set of circumstances, they can undergo physiological changes which impacts their metabolic state, which prevents them growing when they are under undue stress. So we call these viable but non-culturable, or active but non-culturable organisms. So because of the environmental monitoring limitations, and that's something I'll be returning to shortly, we need to make sure that our controls are strengthened. So to loop back to something that I said at the beginning, is that control is always more important than monitoring. Data is of great importance for helping us with risk assessments and for reviewing the results of any environmental monitoring. So we're going to have data in the form of colony forming units, or if we have the luxury of rapid microbiological methods, then we might have things like biofluorescence units. We need to look at that data not just for setting appropriate alert and action levels, and that's something that's always worth trying to get right, because we particularly want to make sure that alert level is set at the right place. But we also need to look at what's the frequency of zeros, and this becomes important particularly in aseptic areas where we'll be hoping to get 98, 99% zero count. So we can use histograms to help us to track any of those sorts of variations with our data. But another important area to trend to look at in the form of data are the types of microorganisms. If we start seeing spore-forming microorganisms, be that fungi or those that are related to bacillus-like species, then that's signalling, again, problems with transfer disinfection. It might be issues with our air handling system, or it might be weaknesses with our cleaning and our disinfection procedures. So characterizing, identifying, trending microorganisms is really important. So this really helps us with investigations. So if we start finding lots of staphylococci, then we've probably got maybe some kind of gowning or operator movement problem. If we start finding Staphylococcus aureus, then that's really concentrated around the nares of the nose. So that might infer weak gown control, for example. So helping with investigations and helping with trending by grouping microorganisms into different types and subtypes is really important. And also reviewing that data helps us with doing things like selecting environmental isolates to challenge our culture media with, or to use for media fields. Remember, Annex 1 says that the media field must have environmental isolates included in it. But also deciding what are the most appropriate organisms to use for disinfectant efficacy studies as well. So these are all important elements that we need to introduce into our review program. So I've got some examples there on the slide. So I've mentioned about staphylococci. We can also introduce micrococci. And similarly, if we were to find streptococci, we would have concerns again with the mask, or maybe an operator's gone in with excessive coughing, or maybe their nose is blocked or something like that. And then we have the spore formers and the importance of trending those. And then if we find gram negatives, well, that gives us a conundrum. So the gram negatives we can approximately divide into two groups based on whether they are fermenters or non-fermenters. So there are certain gram negatives that we would classify as enteric. So they will be coming from within the human body. So they're often the signals for poor personal hygiene. Then there are others that will be associated with water sources. They like particularly dark, damp conditions. So things like water systems, leaks, puddles, that sort of thing. Particularly if we're getting the Pseudomonas type microorganisms, we can put them into that category. For non-steriles, then we would have dilemmas to work through in terms of working out whether our microorganisms are objectionable or not. And this is important because we're trying to work out here, would any potential contaminating microorganism be likely to grow? If it grows a little bit, would it continue to grow? How would this affect the stability of our product? Is this a greater concern if we have a multi-use item? Does it depend upon the population? So is it something that's going to present a greater risk for children or for elderly people? We also need to weigh up whether the impact is minor, so maybe we get a slight coloration change, or we may get a slightly unpleasant odour, to actually putting people at risk of infection or causing them harm. So there's a number of things that we would need to work through in terms of undertaking a risk assessment in this context. And it's going to depend a lot on the likelihood of contamination, the microbial numbers, and so on. But this is a useful loop round to one of the big issues that's been triggered by US FDA, and a lot of this relates to inhalation products. So we have maybe something like this, and that's the risk of contamination from water systems that have been poorly maintained. So this is where the Burkholdia Cepacia complex comes in, this kind of cluster of organisms around these kind of like 30 different biovars that we need to be concerned with. Going back to data, the principles of data integrity are important, so we need to make sure that our data is sufficiently robust, that we can trust our data. And also considering the importance of risk assessment. So are we taking our samples at sufficient frequency? Are our locations of monitoring appropriate? Are those people who are taking the samples appropriately trained? Do they have good competency to do this activity? And then are we transferring the samples back from our manufacturing facility over to our laboratory? Is that being done in the correct way? So data reliability, there's lots of fundamentals to consider. So, we've got things like the type of culture media. Do we, for our environmental monitoring, wish to go out and use two different culture media? So are we going to use like a TSA-like medium and an SDA type medium, so trypanosuric agar, Sabboro's dextrose agar, or maybe an alternative fungal medium like malt extract agar? Or are we going to incubate our culture medium at two different temperatures? If we're going to do two different temperatures, what's the order of incubation that's going to give us the most reliable data? The general consensus with literature and from my own studies is that you would always go for the lower temperature first. That's 20 to 25 degrees Celsius, followed by a 30 to 35 degrees Celsius incubation step. And this is to ensure that we are not damaging and destroying fungi who have lytic cellular enzymes, which can be sometimes sensitive to higher temperatures. There are some advocates who say we can go for a single temperature. I am not one of them. I think the two media or two temperatures is the most important thing for environmental monitoring programs. We also are going to have an impact of equipment as well. So using the right types of active air samplers and particle counters, how we take contact plates and so on. But I'll be looking at that shortly. Maybe there was a power cut. Maybe there was a HEPA filter blocked. Or maybe a room extract wasn't functioning properly, or maybe we saw excessive rises with temperature and humidity. Maybe it was a new shift, a new group of staff. So there's different things we can look at that we can explore to try and make sense of those data peaks. And we need to be mindful of, sometimes we're going to get little fluctuations. It's kind of the big shifts that we want to be focusing on. But it's useful, to get an understanding of what types of excursions, what types of patterns do we want to be most concerned with, and how are we going to follow that up. Not let things drift too far that they become a fundamental. So here's an example of a trend chart. So it's a standard XY chart, or Shewhart chart as some call it. And where we're getting odd data patterns, so you can see on this chart there was a period of time where there were some fairly high bioburden counts within the clean room. These are active air samples taken in a grade B area. And then we get to a point when everything drops down to a low level and we're kind of where we want to be. So investigating why that upward trend happened in the first place is important. So maybe it was maintenance work. Maybe it was the effectiveness of cleaning and disinfection following the maintenance work or in general. Maybe there was a power cut. Maybe there was a HEPA filter blocked. Or maybe a room extract wasn't functioning properly. Or maybe we saw excessive rises with temperature and humidity. Maybe it was a new shift, a new group of staff. So there's different things we can look at that we can explore to try and make sense of those data peaks. And we need to be mindful of, sometimes we're going to get little fluctuations. It's kind of the big shifts that we want to be focusing on. But it's useful, to get an understanding of what types of excursions, what types of patterns do we want to be most concerned with, and how are we going to follow that up. Not let things drift too far that they become a fundamental problem. Okay, so let's consider some of the specific environmental monitoring methods. So I mentioned earlier that, we can't be too reliant upon detection. So the first thing to bear in mind is that not all active air samplers are the same. The suitability of an active air sampler is based on its D50 value. So the D50 value is the given particle size at which we are confident that our air sampler will pick up 50% of the particles passing through it. It then follows that as particles become larger, our ability to detect those particles increases. Therefore, the smallest particle size, when we're comparing, say, two different types of air sampler, is the better model of air sampler to go to. So, for example, if we have an air sampler which claims it has a D50 of 2 micron, this is a better air sampler than one that claims a D50 of 5 micron. And that's all down to the numbers of particles passing through the sampler that we expect to be able to detect. Other things to bear in mind are the effect of dehydration on the culture media when our air sampler, particularly when it's placed under unidirectional airflow, whether our air sampler itself can disrupt the air pattern, or whether it exhausts out contaminations. Factors to bear in mind. With settle plates, then settle plates are very, very important within unidirectional airflow devices. If they're close enough to open products, they will signal the potential for larger particles that are in the air that might fall out with gravitational settling, or where air strikes a particular object, slows down, you get a bit of eddying and something might fall out. Which incidentally is the reason why 5 micron particle counts are of such importance when we're monitoring grade A, because they're more likely to be the microbial carrying particles. Settle plate location, we need to use airflow visualization studies to give us an indication of where the best place is to locate these plates. And there's something else that Annex 1 calls out, which is ensuring that our saddle plates can be exposed for 4 hours without excessive weight loss, without cracking, and so on. So we need to either prove that, hopefully, and use growth promotion testing, or if we have problems, we need to talk to our media supplier and get a better gel or increase the volume within our petri dishes. Contact plates. Contact plates should contain neutralizers. So even if we're using apparent low residue disinfectants, there's still a chance that there will be some level of residual disinfectant activity, which could lead to false negative counts. So a good all-round neutralizer, effective against the disinfectants that we're regularly using, is important. It's also important to try and standardize the time that we place the contact plate on the surface. So 10 seconds is pretty normal for the industry. And if we can control pressure, then that's good as well. So there are some devices that are available that will standardise the pressure, or if not, we need to train staff not only with the technique, the kind of roll-on, roll-off technique, but also with the kind of level of expected force on the surface, and then to time how long the plate is on the surface for. So this issue of residues is of great importance. It's also important to kind of work with your disinfectant supplier and discuss the residue issue. So what we're trying to avoid is either the presence of a detergent interfering with a disinfectant, or two disinfectants interfering with each other, particularly the point, where we're changing our rotational pattern. So that's something that, we need to be very mindful of. Swabs. So swabs generally do not recover contamination from the surface as well as the contact plate. So this is the reason why swabs tend to be restricted for irregular surfaces or very narrow surfaces. So that could be a window ledge, or if we're going back to aseptic filling, it could be the filling needle itself. Where we have a choice of different swabs available, then we should always opt for moistened swabs, either pre-moistened or ones that we moisten ourselves, and flocked swabs. So this is about the intricacies of the tip of the swab. So the flock swab, where you've got little bits protruding out, is superior to the plain swab. So there's plenty of data that shows that difference in recovery. Particle counting. So with particle counting, many people over the years have tried to look for correlations between numbers of inert particles and potential viable contamination. That relationship is quite hard to determine. But we do need to make sure that we have our particles in the right locations, and that we are using a continuous sampling mode. We also need to make sure that we're using isokinetic probes in grade A, because this avoids particle loss. And one of the key things, one of the things that a lot of regulators focus on, is the length of the tubing. So the length of the tubing should ideally be 1 metre or less. It should be straight where possible, but where it needs to bend, then the distance between those bends should be relatively wide. So we're really looking for 15 centimetres between those different radii, and we want to restrict the number of bends to no more than 3. And a lot of this is captured in the new part of ISO 14644 that was issued last year, part 21, as well as taking into account the calibration requirements that are contained in ISO 21501, part 4. So, important things there. And also to try and do things to avoid contaminating the particle counter, so not spraying glove spray too close, and things like that. We also need to be sure that we can sample in an effective manner, that we're not going to introduce contamination into the area we're sampling, or we're not going to have an operator cross-contaminating our samples. And this becomes particularly important with aseptic filling, when we are sampling grade A conditions. There are some important elements to consider when we're developing our environmental monitoring program. So as we approach shutdowns, it can be important to baseline to work out what our conditions were like before we shut down or maintenance work. So we have a good understanding about the level that we want to return to after the shutdown when we finish the maintenance work. Some advocate some monitoring during shutdowns to try and determine the level of likely endospores. And then when we have maintenance work occurring during routine normal operations, so things break down and so on, we need to approach that by using risk assessment and understanding, the potential for contamination, how we're controlling our engineers, what level of cleaning and disinfection are we going to undertake after the event. And we also need to ensure that we're using change controls, and when we use change controls for things that could impact on the environment, that we're using data and making sure that our environmental monitoring program is suitably adapted for that. So, if we're changing shift patterns, let's say we're introducing 24/7 working, if we need to increase the number of people who are going to be present in a room, if we're ramping up our manufacturing throughput, if we're introducing new equipment, these are all variables that can impact upon the state of the environment. And again, reflecting all of that back into trending is important as well. And also, there's going to be other things where we need to introduce risks. So if we have areas like where we've got the risk of explosion or something, where we've got flammable materials, then we may not be able to take in certain items of equipment. So we need to work out, what are we going to do instead? If we can't take a particle counter in, what might we do in that situation? Annex 1 gives a strong push for us to start using rapid microbiological methods. Now, these still remain relatively expensive, but there are some really useful technologies that are coming onto the market. So we've got biofluorescent particle counters that will differentiate between inert and biologic events. So these are useful for working out things like numbers of people in changing rooms, for understanding the risks between airlocks or even potentially in aseptic filling. And then there are technologies that will look at tiny colonies and tell us how many there are before we can see that with the naked eye. So things like blue light excitation, things like that. Now, data integrity. So data integrity is really important when we're discussing environmental monitoring. So, we need to make sure that we're labelling our samples with all the required details whilst we're in the area. We need to make sure that the people who are counting colonies know what they're doing. So can they tell the difference between two merged colonies, for example? Can they really see those tiny little colonies that sometimes can be on the edge of the agar? And also, we need to make sure that in terms of data integrity, we don't have things like that, which is a cracked agar plate, which has come about by that issue of dehydration under grade A. So that would be a data integrity violation because there might be missing data. We also need to consider whether we want to have second reads as well, so that we have a second analyst verifying what the first analyst has read. That's something which FDA are quite keen on. Other regulators don't necessarily push for that. Data integrity also applies to things like particle counting as well. So we need to make sure that our particle counters are password protected, that there's different user access levels. Passwords need to be of sufficient complexity. We should have an independent administrator, and we should be checking the audit trails on a regular basis, or where we use particle counters for, again, say, batch filling, then with every batch we'd want to be checking that audit trail. There are other things that can help inform us when we're undertaking reviews of environmental monitoring data. So, temperature is important. So we're generally going to be less worried in a cold room than we are in an ambient area. There are some organisms that, of course, can grow and survive in cold rooms, but they're less common and less likely to. But areas that are warmer are going to see a greater increase of bacteria. Areas that are excessively humid are going to have conditions that are going to be favourable for fungi, for example. We've always going to have this balance between what's comfortable for the operator as well, because if we put operators under conditions that are too hot and humid, they are going to sweat more, and that's going to reduce the integrity of the clean room down and lead to greater release of skin detritus, and a chunk of that skin detritus are going to have microbial carrying particles on them. Okay, so let's move on to the kind of final main part, and we're going to look at some investigations and some case studies. So first of all, here's some advice, and I know it's something that Pharmig Chairman David Keane is always keen to state, and this is where we get contamination problems: go into the area. Go and visit, go and look, interview people, work with sufficient numbers of other people, so manufacturing staff, engineering, maybe even R&D staff. Look at the process. How does equipment come in? Where do people go? What items are running when? Look at manufacturing records, so from the batch that we're concerned about compared with a batch that is good. Be holistic, so be very open-minded to different areas where contamination may have come into the area. Sometimes we need to take more samples, sometimes we need to undertake hypothesis testing. So there's always going to be things we can do and data that we wish to collect. It's also important not to rush to conclusions and to sort of stand back and think about the data. So, when did our out-of-limit result occur? Where did it occur? What exactly happened? What was affected? Who was involved? And when we think we've put it right, it's then to say, how do we know that? What are we going to do to assess the efficacy of whatever we propose, whatever kappa that we've come up with? So standing back and having a pause, I think, is again something that I would recommend. And then we've got to try and crack the root cause, or the most probable root cause. So on the screen here are some examples of root causes. So, we're going to have different categories. We're going to have things like people, the way they gown, people, hand sanitisation, people and sampling error, equipment cleanliness or damage, transfer of items, which we've already covered, quality of fabric, the risk of wet equipment from water, drift of clean room parameters. So, in the time available, let's have a look at a case study. So this case study is the presence of fungi, filamentous fungi recovery on our environmental monitoring. Something that we don't like to see, but can happen. So this case study, it relates to aseptic processing. And in this scenario, which is a real scenario, there were 2 successive batch fills that recorded fungi from operator finger plates. The first batch recorded a post-filling machine connection grade A finger plate, and 3 fungal colonies were recovered from the right hand of the operator. With our second batch, again, it was a post-filling machine connection. And with this incident, the operator recovered 2 fungi on the left hand and 1 fungal colony on the right hand side. It's also noticeable that the corridor leading to the film room recovered a fungal count. And it then became apparent that these were all the same fungi. So it's a filamentous fungus, an environmental mould, and it's a fungus, as in this Pityomyces, that's found in soil and in vegetation. So it's likely to come from the outside environment rather than being a kind of fungus that might live and exist in the built environment. So an investigation was performed and a number of things were looked at: aseptic technique, people-related activities, transportation, checking the laboratory as well. So, we start to work through a number of things. Now, this facility had closed-circuit television available, so videos were watched, other environmental monitoring data was looked at, things like raw materials, pre-final filtration bioburden, changing rooms, operator training. And then, looking at the map, how does equipment get in? Where does it go? What are the different stages? What happens in those stages? Are all things that need to be looked at. And then lots of different facts were collected, and we start to work through those. And here it's important to be non-judgmental. But one of the things that stood out was that these items were only double wrapped, and there were more than 2 key transfer steps. So, is there insufficient wrapping and then insufficient opportunity to perform decontamination at the appropriate juncture? So you take all that information, and as part of this investigation, an is not table was used. So you're taking each fact and you're saying, yes, it's a confirmed fact, it's something likely, or no, it's something that we can easily dismiss. It wasn't related to this particular scenario. And then it's important from that to form a problem statement. So the problem statement that was defined was that fungal recovery from post-filling machine connection was found on finger plates, and this followed the introduction of the PubSit filter test. So PubSit is pre-use, post-sterilisation integrity testing. It's one of those requirements of EU GMP Annex 1. And then after this, a fishbone diagram was constructed to help deconstruct the problem. And I'm sure many of you have seen these types of diagrams, but you're breaking them down into different areas and then into different potential causes. So we're trying to whittle away, what may have caused this fungi on these finger plates. And then following that, we move into the looking at the different root causes and running what's called a contradiction matrix. So the idea here is that you take each root cause, you ask a series of questions, and when you get to a no, it's not likely, you can probably eliminate that. And when you end up with a series of yeses, or as represented by ticks on this table, that means it's probably something that is not in total control and may well be our root cause. And in this particular case, remember this is just an example, there were weaknesses of controls around the PubSit kits. The way that these were delivered from a supplier had the opportunity for fungi to be present on the outer wrapping. There were insufficient controls, insufficient wrapping removals, insufficient use of sporicidal disinfectant through the different stages that could lead to the contamination transfer. So we need to set some kappa The primary capper was to get the manufacturer to supply the items triple wrapped, but there are also some controls around improving cleaning and disinfection. And there were, some lessons as well. Environmental monitoring is limited. We need to emphasise the control. There's an array of different microorganisms out there, and it's, if we're not in control, these can be readily transferred into the area. So we do need to be careful of that. Okay, so this is starting to bring the presentation to an end. So I've covered some environmental monitoring fundamentals, some issues around monitoring methods, their limitations, the importance of risk assessment. We've had a look at case study as well. And all of these hopefully are things that you can weigh up and they'll be of practical value for developing your environmental monitoring position papers, your rationales, your policies, your method SOPs, and your various follow-up actions. So, I've been Tim Sandle. I hope you've had a fantastic conference so far, and the rest of it goes really smoothly and exciting. And I'm going to have a quick change, and let's go to the Q&A.